Hello students, welcome to the first lecture on feedback amplifiers. Feedback amplifier can be basically defined as an amplifier which has the connecting lane between its output and input terminal. In the first lecture of this feedback amplifier, we will be discussing about the classification of feedback amplifiers and what is the basic concept behind the negative feedback. So this is the classification of the amplifiers. There are four categories. First is the voltage amplifier, second is the current amplifier, third is the transconductance amplifier, and fourth is the transresistance amplifier. And later on we will discuss about the basic concept of the negative feedback, outcome of the lecture, and some questions which are related with the current lecture. This is the first category of the feedback amplifier, which is voltage amplifier. And you can see in the diagram that there is a input circuitry of the voltage amplifier, which basically contains three components: voltage source Vs, source resistance Rs, and input resistance Ra. We can see from the diagram that we want that whatever voltage which is coming across the transistor has to appear across the input resistance Ri. And since it is a series circuit, we can relate with the KVL circuit, and we know that in series circuit voltage gets dropped across the resistances. So when two resistances are connected in series, where this voltage source should drop across, it has to drop across the Ri, because we want that the input voltage must be on higher side so that it can be transformed or it can be amplified further in the output circuitry. So this certainly generates the first condition or first characteristics, that the value of Ri must be greater than Rs. If the value of Ri is greater than Rs, then whatever source voltage which is coming, it will drop across the Ri, and which is the aim of our voltage amplifier. So the first condition is Ri must be greater than Rs, or ideally Ri is infinity, but practically it is a very large value. This is the output circuit of the voltage amplifier, and as we have seen in the previous case, when we are considering the voltage to be dropped across the Ri, here we are considering that the voltage should drop across the load resistance RL, because we want that output should come across the RL. So what condition or what characteristics it generates? It certainly generates that the value of Ro must be on lower side, or RL must be greater than Ro. So Ro is practically a very less value, and ideally it can be considered as 0, since we want that the value of the voltage should appear across the load resistance RL. And this is the gain function AV. Why we are writing it as AV? Because it is the voltage amplifier, and the voltage amplifier gain becomes the output voltage upon the input voltage. Next category is the current amplifier. So students, before I will discuss about the current amplifier, as we have discussed in the previous case, the input and output circuitry in the voltage amplifier is drawn like a KVL circuit. So start thinking that current amplifier, how it will look like. It should be look like a current source connected with parallel of two resistances, or we can say that the Thevenin's circuit which we have discussed, not exactly the Thevenin circuit, but a kind of Thevenin circuit which we have discussed in the previous slide. It will become a Norton kind of circuit, where there is a current source Is which is feeding the two resistors Rs and Ri. And now we want that the input current II should come across Ri. As we know the nature of the current can come only, or current will flow in the path only where there will be least resistance. So what does it mean? It means that if I want the current to be flown across the Ri, the value of Ri must be less than Rs. So Ri must be less than Rs, or practically it should be less than, or practically it is a very less quantity. Similarly, at the output circuit, when we are having RO and RL, and now this time we want that the load current or the output current should come across the RL. Again, it generates the same condition that the value of RL must be less than RO, or in other words, RO must be higher than RL. In the previous case, in this case also, this is the dependent parameter, and here is the current which is dependent on the input current II, and previously it was the. So here this dependent source is it is controlled by the current II. In the previous case, it was controlled by the voltage VI. So this is the gain. Now the gain becomes the value of the output current upon the input current, obviously. This is a transconductance amplifier. So the transconductance, as the conductance is the inverse of resistance, so the function becomes the output current upon the input voltage. So the transconductance amplifier is basically going to be the mixture of the previous two circuitries. Assume, or start predicting that how the circuitry will look alike. The input has to be the voltage and output has to be the current. So we will take the input circuitry of the voltage amplifier and output circuitry of the current amplifier. Then only we can define the transconductance gain, output current upon the input voltage. Again, I am repeating, the input should be the same as the case of the voltage amplifier, where we have seen that the value of Ri must be greater than Rs, and the output must be the output circuitry of the current amplifier, where we have seen that the RL must be less than RO. So the previously two discussed characteristics are taken directly to draw the transconductance amplifier. So this time this particular value of the constant has changed, and now the GM can be written as the output current upon the input voltage. Next category is the trans resistance amplifiers, and as we have discussed in the previous three cases, this is also going to be similar, because now we are considering the trans resistance amplifier. So resistance is nothing but the proportion of, or the ratio of, output voltage upon the input current. So the input circuitry will now become the same circuitry as we have discussed in the input of the current amplifier, and the output circuitry will certainly become that circuitry which we have discussed in the voltage amplifier. So here is the input circuitry. Again, I is feeding the two resistors, so II must come across the Ri. So it has to be, the Ri has to be less than Rs, and as we can see in the slide, and then the output circuitry will look like the same circuitry which we have discussed in the voltage amplifier, as I already told you, and the voltage should be come across the RL, and hence the value of the RL must be on the higher side, or ideally the RO must be 0 or practically very less. So here the gain of the trans resistance amplifier becomes output voltage upon the input current. So this is the slide which discusses, or which gives the brief introduction about the concept of the negative feedback. Please look at this diagram. Here we have the source, which can be voltage or which can be current. Here is the voltage source. This is the load. This is the A, which is representing the open loop gain of the amplifier. Beta is representing the feedback factor, and this feedback factor, which is, we are assuming that whatever feedback network which we have considered in this particular case, it has to be purely resistive. Why we are using it as resistive? Because we know that the property of the resistance cannot change with time. It is irrespective of the time, the property of the resistance is constant. So if we want that there has to be the same correlation between the output voltage and the feedback voltage, then this has to be the purely resistive feedback network. The other components are, this is the voltage source which is coming here, this is the Vi which is the input voltage of the amplifier, this is the Vo which is the output voltage, and this is Vf which is introduced here, which is the new term, which is the feedback voltage. And the feedback voltage depends on how much feedback which we are taking from the output, and it depends on the feedback parameter beta. So now this is the summer circuit. In the later lectures, it will it will be known as the mixer circuit. Since we are not introduced with the topic of mixer and sampler, will be discussed in the coming lectures. So here I am using the word summer circuit. So the actual input Vi becomes, what will be the Vi? Vi becomes Vs minus Vf. Why minus? Because the Vf is connected with the negative terminal of the summer, and since the feedback is connected with the negative terminal of the input port, it is known as the negative feedback. So starting with the open loop gain or gain without feedback is nothing but Vo upon Vi. What is the Vf? Vf is the feedback voltage, and feedback voltage is certainly the multiplication of these two values, Vo into beta, where beta is the feedback factor, or we can say that beta defines as Vf upon V0. So practically beta lies between 0 and 1, 0.3, 0.4, 0.5 depending upon the value which we want at the input side from the feedback circuit. If beta becomes 0, then there is no feedback available, because we have disconnected the feedback network. And if beta becomes 1, whatever the value which is coming at the which is appearing across the output, it will come across the input. So this is the ideal cases. Practically the beta value lies between the 0 and 1. I already told you that the resistive network, we are using the resistive network for the feedback to avoid any phase shift, so that Vo and Vf becomes in phase. So this is the small derivation which will characterize the gain of the negative feedback and how it is related with the open loop feedback or the gain without feedback. So starting with the actual input Vi, as we can see that Vi is Vs minus Vf. So Vs can be written as Vi plus Vf, and this Vf, which is the feedback voltage, it can be replaced from here, from this equation, that is beta into V0. And if we generally if in general terms, if we want to define the gain with feedback, then it has to be Vo upon Vs. It can be correlated with the AVS, which we have already read in the first unit, and in that case we have already seen that AVS is nothing but the gain with voltage source Vs. So here AF, which is the gain with feedback, it has to be equal to Vo upon Vs. Moving ahead, we can write that Vf equals to Vo upon Vs. We have replaced the value of Vs from the previous equation, and Vs can be written as Vi plus beta V0. For simplification, we can divide the numerator and denominator value with the input voltage Vi. So here I am writing Vo upon Vi, here Vi gets 1, beta V0 upon Vi. V0 upon Vi, what is V0 upon Vi? V0 upon Vi is the first equation which we have considered in the previous slide. It is the open loop gain or gain without feedback. So ultimately this equation comes like AF equals to A upon 1 plus A beta. So this is the D sensitivity factor, which is known as the D, which will be discussed in the later lectures. So what this particular equation suggests, that AF can be either less than A or it can be equal to A, but it can never be greater than A. How? If beta becomes 0, if there is no feedback available, then the open loop gain or the gain without feedback becomes equal to the gain with feedback. And if there is any factor beta, then this particular value becomes on the higher side, or we can say that the gain with feedback becomes less than the gain without feedback. So what are the takeaways from this particular lecture is the feedback, the negative feedback stabilizes the gain. How it stabilizes the gain? Because it desensitizes the gain. When I'm saying it is desensitized the gain, it means that the gain becomes constant irrespective of the changes in the input parameters or in the temperature parameters or in the, practically there are some non-linearity, practically there are some variations, but ideally we can say that it stabilizes the gain. And since we are controlling and feeding the input network from whatever value which is coming across the output through the feedback voltage VF, so we are ultimately controlling the output voltage. It also increases the frequency response, or the extension of the bandwidth is provided by the negative feedback, because there is a very important terminology, gain bandwidth product. And for any amplifier, this gain bandwidth product must be a constant value. So if I'm saying that the negative feedback reduces the gain, so to maintain that constant value, the bandwidth must be on the higher side. So the outcome is the frequency response will be improved if we are using the negative feedback. Third important property is third important advantage is the noise reduction. Again, it is related with the stability of the gain, since we are feeding the value from the output to the input. What about the noise value that gets reduced at the input terminal? It will also increase the linearity of the amplifier, because the gain becomes constant and independent of the signal level. So more linear operation we can expect from the amplifier with the negative feedback. And it also control the input and output impedances. How it will be seen in the upcoming lectures. So what we have discussed in this particular lecture is the types of the feedback amplifiers, their basic characteristics, what is the relation between the input and output impedances, how they are related with the source resistance and the load resistances, and what is the basic concept of the negative feedback, how negative feedback is helping the improvisation of the transistors and transistor amplifiers characteristics. What questions we can expect from this particular lecture? It is nothing but the feedback amplifiers type, their basic circuit diagrams, what are the advantages of feedback negative feedback amplifiers, and how it improves the performance of the amplifier. Likewise, the similar questions we can consider in the examination. In upcoming lectures, we will discuss in more detail that how we can derive the equations of input and output impedances of the different category of amplifiers, which we have discussed in particular lecture. So stay tuned for the more updates. Thanks for watching.